Welcome back. This is another short segment in which I want to give you a different taste of recursion. And this has to do with the way we can define sets in a recursive or an inductive way, which is a little bit unusual. So let's think of a set as something that starts empty and then that you build up by adding elements one at a time. So what I want you to think about now is the following set S, which is defined by the following rules. So remember, think of it as an empty set, and then we're going to use the rules to add elements to this set one by one. And the question I want you to think about is, what is that set S that is defined by the following rules? So the first rule, R1, says that the integer 2 is in S. So this is just a rule that states, okay, you can go ahead and put the single element 2 in a set S. The second rule, R2, states that if you already have an element n in S, then the element obtained by adding 2 to it is also a member of S. So you can also add n plus 2 in the set if you already have n. So what's the difference between those two rules? Well, this rule is basically a base case. It doesn't depend on anything else, whereas this rule actually assumes there's already at least one element n in the set and uses that element to produce another new element in the set. So this is like a recursive or an inductive rule, whereas this is like a base case rule. And the third and last rule simply states that there's no other way to add anything to the set S beyond rules R1 and R2. So these are the only three rules that you can use to add elements to the set S. So again, my question is, can you define mathematically what the set S is? So the short answer is that S is the set of all the positive even integers, 2, 4, 6, 8, 10, 12, etc. It's an infinite set. So how could that be? Well, you are really allowed to apply rule 1 only once, since once you put 2 in the empty set, you get a singleton set with the element 2, and then you're never going to be able to do anything else with this rule. Sure, you could apply it again, but adding the same element to a set where it already belongs doesn't change the set, as you know. So the key rule here is this inductive or recursive rule, because now that there is an element in the set S, namely 2, we can call that element n, and now we can add, according to R2, the new element 2 plus 2, which is 4. But now that 4 is in the set S, n can take on the value 4, and therefore you can add the integer n plus 2 equals 6 to S, and so on and so forth. What you need to remember is that n here in this rule is just a dummy variable that stands for any element that's already in S and allows you to add a new one at a time. But because you can do that forever, you can always add the next even integer to the set. S is the infinite set of positive even integers. So that's a little bit unusual way of defining that set, but it's definitely a valid way of doing so, and it comes pretty handy in some context, and in particular later on in some computer science courses, you might define sets inductively like this. Now, of course, there are always many ways to define the same object. So here, we could define the set S inductively in many different ways. Here is a second definition of S by induction. So it's going to be a set of rules again. In fact, the first one of which is the same as in the previous definition. The difference here is in the second rule. It says, if m and n are already in S, then so is the sum of m and n, m plus n. So this says if you can find a value for m and a value for n, then you can add a new element to the set, which is the sum. And let's not forget the third rule that says you're not allowed to use any other rules to add elements to S. This is to guarantee that someone doesn't come along and maybe add the number 3 in there. And that would mess up the definition of S as the set of positive even integers. So let's convince ourselves that this definition is also a definition of the same set S, where clearly, according to the first rule, you can add the integer 2 to the empty set. And now that you have the element 2, you can assign the value of 2 to both m and n, and therefore you can add the integer 4, 2 plus 2. And now we have a set with 2 and 4. So we can pick m to be 2, n to be 4, and we can add the integer 6. Now we have 2, 4, and 6 in the set. So of course we could take m to be 6, n to be 2, say, and now we have the integer 8 that we can add into the set. And so on and so forth. You could see that this is a different way of generating the same set S. So later on, when we use this inductive or recursive definitions of set, you will typically be able to pick among different such definitions for the same set. Now, which one is better than the other? Well, the answer is typically it depends what you're trying to do. In particular, picking this definition over this one, or vice versa, may make it easier for you to prove a property of the set S. So in short, you always pick the definition that makes it easier for you to prove the property of the object that you're trying to prove. But that's all we're going to say about recursive or inductive definitions of set for now. This is just to give you another example of a recursive object besides recursive functions.